All right, so we need to find the eigenvalues and a basis for each eigenspace for this matrix. So we'll find the determinant of A minus lambda I, and that just means we're going to find the determinant of the matrix where we subtract lambda from the main diagonal. So we get 1 minus lambda, 5, -2, 3 minus lambda. All right, so we multiply the diagonal, 1 minus lambda, 3 minus lambda, and then subtract the other diagonal. It's going to be plus 10. All right, so just fold this out. And simplify. So I get lambda squared minus 4 lambda plus 13. So if you check, this trinomial can't be factored in the usual way. So we're just going to solve this by, let's complete the square. So I'm going to move the 13 to the other side. B over 2 is -2. If we square that, that's 4. So we need to add 4 to both sides. And this is a perfect square, lambda minus 2 squared. And now we take the square root of both sides. And when you take the square root of -9, that's a complex number, imaginary number. So we get plus or minus 3i. And then we add 2 to both sides. We get 2 plus or minus 3i. So we have, in this case, complex eigenvalues. So how do we deal with that? Well, we're going to do the same thing that we did before with real numbers. It's just going to be a little bit different when we solve for the eigenvectors. So let's say for the first eigenvalue, 2 plus 3i, and these always come in conjugate pairs, by the way, right? So you always have a plus or minus in the middle there. We need to solve a minus 2 plus 3i times identity I times the eigenvector x equals 0. We're going to solve for x. So this matrix means subtract 2 minus 3i from the main diagonal. So let's look at our matrix. We got 1, 5, -2, 3. And we need to subtract 2 plus 3i from the main diagonal. And then we augment that with 0. So we just need to simplify this. Let me move this 5 over so it looks better. There we go. So 1 minus 2, that's -1. We're also subtracting the 3i. So we get minus 3i. And then 5. -2. And this one is 3 minus 2 is 1. And minus 3i. All right, so the question is, how do you row reduce a matrix like this that has these complex numbers in it? Well, really we'd like this guy to be a 1. So let's turn this complex number into a real number. So how do you do that? Well, you just need to multiply this complex number by its conjugate. So I'm going to multiply row 1 with row 1 times the conjugate of that number. So I'm going to say replace row 1 with -1 plus 3i times row 1, and the plus 3i makes it the conjugate. All right, so let me just do this multiplication here separate. So what happens if we multiply these two together? So I get plus 1. Here I get minus 3i. Here I get plus 3i. So those cancel out. That's that's going to get rid of the i's. That's what's going to make this a real number. And here I have negative 9 I squared. And again, I squared is a real number, right? I squared is negative 1. So this is 1 plus 9, which is equal to 10. So if I multiply this row by negative 1 plus 3i, I'm going to get 10 in the top left corner. And this 5 is just multiplied by negative 1 plus 3i. And I've got the negative 2 and the 1 minus 3i here. Okay. So, we could go about this a few ways. We got to get a 1 and a 0 in this column. It really doesn't matter which one gets the 1. If we make this a 1, then we'll just switch the rows. So if you could see, though, if I multiply this by 5 and add it to the first row, I'll get a 0 here. So let's do that. So I'm going to replace row 1 with row 1 plus 5, row 2. This column of zeros is not going to change. This is not going to change. So if I multiply negative 2 times 5, I'll get negative 10, and add it to 10, I'll get 0. And if I multiply this by 5, if you look at these, this is negative 1 plus 3i, this is 1 minus 3i. If I add those together, I get 0, right? So if I multiply this by 5 and add it to this, I'm going to get 0 here as well. So now we just need to switch the row and divide by negative 2. So I'll put the row zeros on the bottom, divide negative 2 by negative 2, I get 1. If I divide this by negative 2, I get negative 1/2 plus 3/2 I. All right, so that is row reduced now. I've got a basic variable and a free variable. So that means x1 is equal to the negative of negative 1/2 plus 3/2 I times x2. x2 is free. So let's multiply this negative inside. So that would be positive 1/2 minus 3/2 I times x2. So you can pick anything you want for x2. I just say pick something that makes sense. So let's let x2 be 2, and then that will cancel these fractions out. All right, so we get an eigenvector. Let's call it v. We're using too many x's here. We'll call this eigenvector 1. x2 is 2. If I plug in 2 here, it's going to cancel these fractions over 2, and I get 1 minus 3i. So there we go. We have a complex eigenvalue, and now we have a complex eigenvector. All right, so let's see what would happen if we do the other eigenvector or eigenvalue. Let's find the other eigenvector for the other eigenvalue. So for this one, we did 2 plus 3i, so this one's going to be 2 minus 3i. So we're going to go through the same process. I need to subtract lambda, which is 2 minus 3i, from the main diagonal, and augment with 0. So let's say I keep forgetting the original matrix. 1, negative 2, 5, 3. We have to subtract 2 minus 3i from the main diagonal, augment with 0. So let's simplify. So 1 minus 2 is negative 1. Minus negative 3i will be plus 3i. Very similar to what we got last time. -2, and then 3 minus 2 is 1, and then plus 3i. Okay. So we're going to do something very similar here. Let's make this a real number. Going to multiply by the conjugate. So -1 minus 3i. I already know what that is because we multiplied that here together, right? -1 minus 3i, -1 plus 3i is 10. So if I multiply these, I'm going to get 10, and I'll get 5 times -1 minus 3i. If I multiply this by 5 and add it to the first row, I'm going to get 0 here. Am I going to get 0 here? Yeah, these signs are all switched. This is the same thing as -5 times 1 plus 3i. So if I multiply this by 5 and add it to this guy, they're going to cancel out. I'm going to get zeros. And I just need to move the second row to the first row and divide it by -2. Right, so it looks almost exactly the same, and it is almost exactly the same, but there is a difference here, and so we'll look at that. So we've got basic variable x1, free variable x2. So x1 is the negative of this, which would be 1/2 plus 3/2 I times x2, and x2 is free. Let's let x2 be 2, and it will cancel these fractions. I get 1 plus 3i. So our second eigenvector will be 1 plus 3i, 2. And what was our first one? Our first one was 1 minus 3i. You can see that our eigenvectors are conjugate pairs as well. And you might be asking, well, does this happen every time? And the good news is yes, it happens every time. So we actually didn't have to do all of this work here. I just did it to show you. But all this work we did for the second eigenvector, you could have just gone from here to here, because from now on, you're going to know that your eigenvectors for conjugate pair eigenvalues will be conjugate pairs as well. So you just need to take the conjugates of any complex numbers in your vector, and you can just create another vector that will be the other eigenvector. So that's how you deal with complex eigenvalues.